Good evening, Dr. Phil here. Today we will be discussing on the measurement of carbon dioxide. A capnometer is a device that measures the partial pressure of carbon dioxide in a gas sample and displays the result in numerical form. A capnogram is a graphical plot of carbon dioxide partial pressure or percentage versus time, and types of presentation includes the time capnography, where x-axis is time and y-axis is PCO2, and volume capnography, where the x-axis is the tidal volume and y-axis is the PCO2. The time capnography is more popular than the volume capnography. A capnograph is a device that records and shows the graphical display of the waveform of CO2. The value of CO2 at the end of the expiration is known as the end tidal CO2. Methods of measuring carbon dioxide. Infrared absorption. This is the main method of carbon dioxide measurement in the operation theatre. Both inspired and expired carbon dioxide concentration can be measured continuously. The principle is, any molecule that contains two or more different atoms will absorb infrared radiation at 1 to 40 micrometers, for example, carbon dioxide, nitrous oxide, and other anesthetic inhalational agents. The components of the system includes an infrared source, a filter that allows only radiation of the desired wavelength to be transmitted, a crystal window, a sample chamber, which can be mainstream or side stream, a reference chamber that contains the reference gas sample, which is usually room air, and photodetector, which measures the light reaching it from the infrared source after passing through the sample or reference chambers. Regarding the sample chamber, a mainstream sample chamber is positioned within the patient's gas stream, and a side stream sample chamber is connected to the distal end of the breathing system via a sampling tube. This table compares and contrasts the two types of analyzers. A side stream analyzer consists of a sampling tube of 1.2 mm internal diameter and samples the gases, both inspired and exhaled, at a constant rate of 150 to 200 mL per minute. The tube is connected to a lightweight adapter near the patient's end of the breathing system, as shown in this diagram. The closer the sampling tube is to the trachea, the more accurate is the measured EtCO2. A pneumotachograph for spirometry is included. There is a small increase in the dead space. It delivers the gases to the sample chamber, and it is made of Teflon, which makes it impermeable to carbon dioxide and does not react with anesthetic agents. A mainstream analyzer, on the other hand, the sample chamber is positioned within the patient's gas stream, and this increases the dead space, as shown in this diagram. Time delay in gas analysis. In the side stream analyzer, there is a time delay in gas analysis. The response time depends on the transit time and the rise time. The transit time depends on the length of the sample tube and increases with increasing length of the sample tube, which should be as short as possible. The rise time is the time for the analyzer to respond to the signal and depends on the optimal flow rate and the size of the sample chamber. A very low flow rate and a large sample chamber increases the rise time. A time delay of less than 3.8 seconds is acceptable. There is no time delay in the gas analysis of a mainstream analyzer. This connection is possible in the side stream analyzer and also in the mainstream. Sampling catheter leak is common in the side stream but not common in the mainstream analyzer. There is a moisture trap in the side stream analyzer. A moisture trap with an exhaust port allows gas to be vented to the atmosphere or returned to the breathing system. In the mainstream analyzer, there is no moisture trap but it is heated to 41 degrees Celsius to avoid water vapor condensation on its windows. Water vapor condensation on the sensor can result in false high carbon dioxide readings. Calibration of gas is required in the side stream but not the mainstream analyzer. Sensor damage is not common in the side stream analyzer, but it can occur in the mainstream analyzer. Multiple gas analysis is possible in the side stream but not the mainstream analyzer. The side stream analyzer can be used in non-intubated patients but not for the mainstream. Portable handheld devices is available for the side stream but not the mainstream analyzer. The side stream analyzer is lighter and less cumbersome compared to the mainstream analyzer, which is heavier at the patient's end of the breathing system. Mixing of sample gas and inspired gas occurs in the side stream but not the mainstream analyzer. Carbon dioxide absorbs infrared radiation maximally at a wavelength of 4.3 micrometers. The sample chamber. The amount of absorbed infrared radiation is proportional to the number of carbon dioxide molecules in the gas sample. The remaining unabsorbed infrared radiation falls on the photodetector, which is a thermopile detector, and heat is produced and measured by a temperature sensor. The amount of carbon dioxide present is inversely proportional to the amount of infrared light detected at the photodetector. The heat generated is proportional to the partial pressure of the carbon dioxide present in the gas sample, and this produces an electrical output. Similarly, infrared light passes through the reference chamber, which contains room air, periodically, and its amount is detected by the photodetector. The purpose is for calibration against zero with a known carbon dioxide concentration to avoid drift. The amount of infrared absorption is compared between the sample and the reference chamber, and carbon dioxide values are calculated. Inspired and expired carbon dioxide forms a capnograph. Microprocessor-controlled infrared lamp produces a stable infrared source and a constant output. The current produced is measured using a current sensing resistor, and respiratory rate is calculated using the rise and fall of carbon dioxide during the respiratory cycle. Alarm limits can be set for low or high values. Issues affecting the accuracy of the measurement. EtCO2 will not be accurate in patients with COPD, where there is a sloping expiratory trace as the alveoli empties carbon dioxide unevenly. It is difficult to interpret EtCO2 in the pediatric population due to the high respiratory rate, small tidal volumes, and mixing of tidal breath with fresh gas. Dilution of EtCO2 can occur in system leaks. Carbon dioxide and nitrous oxide has a similar infrared light absorption profile for which modern instruments can compensate. Without compensation, falsely elevated carbon dioxide readings will occur as a result of collision broadening. A high oxygen concentration can falsely increase pCO2 as well due to the broadening effect of oxygen on the light absorption. A correcting factor that is built into the monitors can correct for this. Photoacoustic spectroscopy. In this method, sample gas is irradiated with pulsatile infrared radiation, and periodic expansion and contraction occurs. This produces a pressure fluctuation of audible frequency that can be detected by a microphone. It is extremely stable, and calibration remains constant for longer periods of time, and it has a fast response time. The next method is calorimetric measurement of carbon dioxide. Carbon dioxide and water forms carbonic acid, and carbonic acid changes a pH-sensitive color indicator from purple to yellow when the pCO2 is more than 15 mm mercury. Advantages includes it is small, lightweight, inexpensive and disposable, and it is used to confirm correct endotracheal tube placement when formal capnography is unavailable. Mass spectrometry can be used to measure carbon dioxide. It is an extremely accurate technique with a rapid response time, and simultaneous measurement of different compounds is possible. Disadvantages includes it is a large and expensive device, and it is not routinely used in operation theatres. Mechanism. The gas sample is introduced into an ionization chamber. Some of its molecules pass through an electron beam and becomes charged. Ionized particles are then accelerated out of the chamber to reach a strong magnetic field. The magnetic field deflects the particles according to their mass. Ions that are too heavy bends less than those that are light, and only ions of the right mass enters the detector. The molecules of interest is detected and recorded on a display. Raman effect. Raman spectrography exploits the ability of carbon dioxide to scatter light emitted by an argon laser beam. When electromagnetic radiation interacts with a molecule, partial or complete transfer of energy may occur. Intermolecular bonds absorb the energy. Some of that energy is re-emitted at different wavelengths, and the decrease in wavelength is characteristic of the individual molecule. By measuring the decrease in wavelength, which is characteristic of that individual molecule, the molecules can be quantified. Indications for capnography. Confirmation of proper placement of airway devices. The American Hospital Association guidelines states, continuous waveform capnography is the most reliable method of confirming and monitoring correct placement of an endotracheal tube. Examples of airway devices include single lumen or double lumen endotracheal tubes, supraglottic airway devices in situations of blind nasal intubation, tracheostomy tubes. It has better sensitivity and specificity than auscultation of the chest post-intubation. It enables early recognition of misplaced endotracheal tubes, potentially averting death from hypoxia. False negative readings may occur in low-flow states such as cardiac arrest. Firstly, exclude misplaced ETT. Reappearance of PCO2 readings is a good prognostic sign in cardiopulmonary resuscitation. False positive readings is possible with esophageal intubation and occurs in patients who receive prolonged mask ventilation or patients who ingested large amounts of carbonated drinks. Capnograph waveforms in this situation usually fades rapidly after 3 to 5 breaths. The next indication is to monitor ventilation during moderate sedation to general anesthesia. It enables early detection of hypoventilation. It can be used to monitor ventilation in patients receiving ventilatory support in the ICU and enables early detection of leaks, disconnections, valve malfunction, ATT displacement, or airway obstruction. EtCO2 as a surrogate for PaCO2. PaCO2 measurements may result in mechanical, infectious, and thrombotic complications during arterial blood gas sampling, and capnography enables the clinician to avoid these complications, reduce blood loss, and it is more time and cost effective. A study has shown that 90% of samples has less than 10 mm mercury difference between the PaCO2 and PEtCO2. Estimation of the dead space ventilation. The PaEtCO2 gap is the difference between the PaCO2 and the PEtCO2 and is normally 2 to 5 mm mercury. The difference between EtCO2 and PaCO2, alveolar carbon dioxide is less than the PaCO2 because blood from ventilated alveoli mixes with blood from unventilated alveoli and lung parenchyma, both of which have higher carbon dioxide contents. And EtCO2 is less than alveolar CO2. EtCO2 is diluted with alveolar dead space gas from unperfused alveoli. Thus, PaCO2 is higher than alveolar CO2 and alveolar CO2 is higher than EtCO2 in normal conditions. EtCO2 is 2 to 5 mm mercury less than arterial CO2 in healthy adults with normal lungs, and the difference is less if the lungs are ventilated with large tidal volumes. An increased PaEtCO2 gap can occur in various cardiac or respiratory diseases such as pulmonary embolism, hypovolemia, hemorrhage, and excessive PEEP. A negative gap is uncommon. Firstly, verify the validity of the values. Possible causes include low frequency high tidal volume ventilation, post-cardiac bypass, post-physical exercise, pregnancy, pediatric patient, and severe lung disease. The Bohr equation is described in 1890 and attempts to correlate PCO2 and physiological dead space. Dead space is the sum of anatomic and alveolar dead space. Enkhoff modified the Bohr equation by changing the PA alveolar CO2 to PA arterial CO2. The equation is VD divided by VT, which is a physiological dead space divided by tidal volume, equals to PaCO2 minus PETCO2 divided by PaCO2, where PaCO2 equals to alveolar partial pressure of carbon dioxide and PETCO2 equates to partial pressure of end-tidal carbon dioxide. The next indication is confirmation of proper placement of feeding tubes for enteral nutrition. If a capnography trace is present, then the feeding tube is misplaced in the trachea and should be repositioned. Detecting cardiovascular or respiratory conditions, we will discuss this further in the next section of capnography traces. Confirmation of brain death. Regarding the apnea challenge test, this test is positive if there is a lack of spontaneous ventilation when apnea-induced hypercapnia of more than 60 mm mercury occurs. Last indication is to prognosticate ARDS. An increased PA-EtCO2 gap in early ARDS is a risk factor for death. The normal capnograph trace. Expiratory phases includes phase 1, 2, and 3, and inspiratory phase 0. In phase 1, it is initiated at the start of the expiratory phase and has a low plateau and represents the washout of the anatomic and circuit dead space, which is usually lacking in carbon dioxide. This is phase 1. In phase 2, it consists of an S-shaped upstroke curve. PCO2 readings increase during this transition phase from low to high carbon dioxide content as the gases originating from the alveolar spaces, which is high in CO2, progressively washes out the gases from the dead space, which is low in CO2. Changes in perfusion affects this phase significantly. This is phase 2. Phase 3 consists of a slow rising high plateau and represents carbon dioxide drawn from the alveolar units. A slow rising plateau occurs instead of a flat horizontal plateau because there is a variable rate of diffusion of carbon dioxide from the different alveolar units. These units have different ventilation perfusion ratios. A flat horizontal plateau will only occur if all units had equal VQ ratios. The phase 3 slope is affected by increased airway resistance and changes in ventilation perfusion ratios. And the uppermost point of the PCO2 in the phase 3 is the PETCO2. This is phase 3. Phase 0 initiates at the transition between expiration and inspiration and consists of a sharp decline and return to the low baseline. This phase ends with the initiation of a new inspiration where phase 1 starts again. This is phase 0. There are two angles, alpha angle and beta angle. Alpha angle is the angle formed between the lines representing phase 2 and 3, which is normally 110 degrees. Alpha angle is affected by the overall ventilation perfusion status, variations in time constants within the different alveolar units, cardiac output, airway resistance, and functional residual capacity. The beta angle here is a straight angle formed between the lines representing phase 3 and 0 and is commonly affected by rebreathing. The capnograph displays a new PETCO2 and PiCO2 for each respiratory cycle. Abnormal capnograph traces. This is a normal capnograph at the respiratory rate of 12 per minute. In obstructive airway disease, there would be a slurred upstroke as the lung units empty slowly in the obstructive airway disease and EtCO2 is raised as a feature of the underlying disease. Rebreathing. Baseline is not 0. EtCO2 may rise. The patient may hyperventilate if breathing spontaneously to wash out the CO2. Check for exhaustion of soda lime in a circle system. This curve shows inadequate paralysis. During the plateau phase, a large cleft occurs as the patient makes a transient respiratory effort to draw fresh gas over the infrared sensor. Cardiac oscillations is usually seen during bradypnea. During the prolonged expiratory pause, the mechanical pulsations of the heart forces small quantities of alveolar gas out of the lungs, and alveolar carbon dioxide is detected as transient spikes by the infrared sensor. Obesity or pregnancy. A small rise at the end of the rising plateau phase is attributed to fast and slow emptying alveoli with different time constants. EtCO2 that falls over the course of a few breaths. If there is an instant fall in EtCO2, it could be due to disconnection, tracheal tube displacement, auto-calibration or equipment error. A rapid fall in EtCO2, such as in this graph, it could be due to acute loss of cardiac output, such as in pulmonary embolism or shock, esophageal intubation, and if there is circulatory arrest, a flat trace will be seen. If there is a gradual fall in EtCO2, it could be due to hyperventilation. This curve shows a rapid breath-to-breath increase in EtCO2 due to an increased carbon dioxide production from increased metabolism and is typical of malignant pyrexia. Breathing system disconnection. There is an acute absence of the capnography trace. Hyperventilation. There is short respiratory cycles coupled with a lower EtCO2. Hypoventilation. There is longer respiratory cycles and a higher EtCO2. For high EtCO2, possible causes includes hypoventilation, rebreathing, sepsis, malignant hyperpyrexia, hyperthermia, skeletal muscle hyperactivity, and hypermetabolism. Decreased EtCO2 causes includes hyperventilation, pulmonary embolism, hypoperfusion, hypometabolism, hypothermia, hypovolemia, and hypotension. These are my references. Thank you.